Okay, part two of the discovery of acetylcholine and the great soup versus spark debate from my endocannabinoid graphic novel series based on Moby Dick. But before we can resolve the soup versus spark engagement, we must step back even further in neural history to the close of the 19th century, where another stirring call to arms and scientific truth eventually saw another truce with an uncanny resemblance. Two scientists named Camillo Golgi and Santiago Ramon y Cajal shared the 1906 Nobel Prize for their work on the structure of the nervous system. Despite the fact that the two championed diametrically opposed viewpoints about the workings of the brain, Golgi stood for the reticularist doctrine. Using a silver staining technique that still bears his name, he saw in the brain tissue under his microscope a structure appearing to consist of one continuous and undifferentiated network. He declared the whole brain to be an unbroken 3-pound web of filaments and awareness consisting of no internal walls, similar to the tremendous mycelium in one of those mushrooms sprawling across hundreds of acres. Unfortunately for Golgi, though many initially sided with him in those early days of microscopes too coarse for the finer details of neuroanatomy, as the evidence eventually rolled in and the fog started to clear, the victory went to the neuronal theory of that master visualizer, patient artist, and neurochemical hero, Dr. Ramon y Cajal. Ramon y Cajal described a brain composed of many individual neurons, akin to a network of autonomous city-states, built closely together as tight as tenements, but separated by infinitesimal gaps, now known as synaptic clefts. His dogma prevailed. No neuron touched its neighbor, and any information passing between them must be somehow bridging across those narrow spaces between their cellular walls. But what kind of signal? The 1900s opened with that age's great neural debate of scientists arguing with a furious force about whether the neurons communicated via the slow diffusion of chemical messengers, soup, or the fast firings of electricity, spark. The two opposing camps set up the typical loggerheads of opposition, complete with nasty remarks, severed friendships, and barrels of letters in scientific journals, almost pickled in disbelief at their colleagues' staggering blindness to the data and their pig-head resistance to seeing the way things obviously work. The solution came through acetylcholine, the first discovered neurotransmitter and an excellent example of how all of this works. And it came about because of one of the most famous dreams in scientific history. On the night before Easter Sunday of 1920, Dr. Otto Lowy, a German-born pharmacologist and psychobiologist, said he awoke, turned on the light, and jotted down a few notes on a tiny slip of thin paper. Then I fell asleep again. It occurred to me at 6 in the morning that during the night I had written down something very important, but I was unable to decipher the scrawl. The next night, at 3, the idea returned. It was the design of an experiment to determine whether or not the hypothesis of chemical transmission that I had uttered 17 years ago was correct. I got up immediately, went to the laboratory, and performed a simple experiment on a frog heart, according to that nocturnal design. In an experiment that still ranks as a staple of high school lab classes, he places two still beating frog hearts next to each other in their own chambers. And if you don't know, if you remove a frog's heart and put it in saline solution, it will pump away happily for a few hours. On one of these hearts, it still has the vagus nerve intact. Thanks to Galvani a century earlier, Lowy already knew that stimulating the nerves of a frog's leg with electricity would make the muscles fire and twitch the leg. And the same was true of the heart. If you electrically stimulated certain input nerves, the beats per minute increased. If you stimulated certain other ones, such as the vagus nerve, the contractions slowed down instead. This second heart had no vagus nerve. It was denervated. When Lowy applied electrical stimulation to the vagus nerve of the first heart, it slowed down. He then took some of the liquid from that beaker and placed it in the beaker of the second heart. And then it too slowed down. From this liquid, he isolated the inhibitory factor, a molecule he named Vagustov. As the short, sweet essay, Otto Lowy, Dreamer and Nobel Laureate by McCoy and Tan say, Lowy's dream thus led to the discovery that the primary language of nerve cell communication is chemical, not electrical, and won its dreamer the Nobel Prize in Medicine. Plus, Lowy suspected that Vegas-Toff might be the same molecule described for the past several decades as acetylcholine, a molecule that in 1913 made his colleague Sir Henry Dale say it made him perilously near wild theorizing. That chemical story of acetylcholine began in 1867 with Alfred von Baeyer. Amidst a long career of chemical discoveries and creations, including formaldehyde, phenol, indigo, and barbiturate acid, which is the parent of the barbiturates, the German chemist determined the structure of acetylcholine and its precursor choline, synthesizing them both in his lab. For the first known evidence of biological effect directly attributed to acetylcholine, Reed Hunt and René de Tavaux in 1906 found that exceptionally tiny doses decrease an animal's blood pressure. In the paper, they theorized that because acetylcholine is a substance of extraordinary physiological activity, and in fact, I think it is safe to state that as regards its effect upon the circulation, it is the most powerful substance known. And I'm inclined to think that it is due to an effect upon the terminations of the vagus nerve in the heart. So already, 25 years before Lowy's dream, did the theorizing circle around a chemical component of nervous signal transmission take place. Then, in 1914, Arthur Ewens and Sir Henry Dale discovered the first evidence of acetylcholine in nature. So far, it had all been about measuring the effects of this compound made in the lab. But when a batch of ergot fungus, which is also the source of ergotamine, the precursor of LSD, came in with a rare contaminant, Dale tasked Ewens to figure out what it was. Thanks to this lucky accident of contaminated fungi, as Dale called it later in his life, he wrote at this time to his friend T.R.R. Eliot saying, "We got that thing out of our silly ergot extract. It is acetylcholine and a most interesting substance." The next year, Dale wrote a wide-ranging paper on the pharmacology of the molecules derived from choline. He pointed out some of the primary effects of acetylcholine could be reproduced by injections of muscarine or nicotine. So that was the state of acetylcholine and the chemical transmission of nerve signals in the early 1920s. The idea was in the air of some labs, but Lowy's dream met stiff resistance. Many criticized Lowy's methodology around his so-called Vegas-Toff. He traveled widely for years, demonstrating the experiment at scientific gatherings to his colleagues. A turning point came at the 1926 International Congress of Physiologists. According to Tansey, performing the experiments there provoked almost a chain reaction of renewed interest in the possibility of chemical involvement in neural functioning. Further work from Lowy and his colleagues showed that Vegas-Toff was a choline ester that was rapidly hydrolyzed, broken down, by an esterase, an enzyme. Then 3 years later, in 1929, Dale found acetylcholine in the organs of mammals. But the key to working out the function of acetylcholine lay in leeches. And the method man who discovered the key was a refugee of Nazi Germany. Dr. William Feldberg worked as a physiologist in Berlin, but with the purge of Jews from their jobs, it was only after meeting Dale at a conference in Wiesbaden that they agreed for Feldberg to move to Dale's laboratory in Hampstead. The two shared a similar outlook about the importance of perfecting the method of testing before carrying out the experiment. For Feldberg, it became one of the aphorisms of a long career. Die Method ist alles. The method is all. As Tansey described it, the leech test pioneered by Feldberg revolutionized the analysis of the role of acetylcholine. Feldberg's key was the use of eserine, which inhibited the activity of the enzyme that broke down acetylcholine. When you add it to an organ bath in which a leech muscle is suspended, the muscle became extremely sensitive to acetylcholine, and thus it became a simple and sensitive assay for the detection of acetylcholine. This led to a flurry of studies across the 1930s, 24 of them bearing Feldberg's name, on how acetylcholine caused neural transmission and muscle reactions. But still, vigorous opposition arose to this chemical neurotransmission model, especially by Dr. John Eccles, soon to be a Nobel Prize winner, who still believed in the purely electrical transmission of nerve signals. The soup versus spark debate continued to rage across the literature and in the meeting. But as the decades wore on and the evidence built up, even the hardened critics switched to this chemical theory of neurotransmission. On the occasion of Sir Henry Dale's 90th birthday, his great scientific opponent offered this tribute. My memory takes me back more than 3 decades when Dale and his colleagues literally staggered us neurophysiologists by the hypothesis that even the fast synaptic transmission were mediated chemically. After many years of resistance to this hypothesis, I came in 1951 to accept it unreservedly by what Sir Henry regards as the scientific equivalent of a religious conversion. I reciprocate appropriately by saying that he is one of my scientific saints. The soup versus spark debates were over. And a touching turn of events just before Dale's death at the age of 93, in 1968, two scientists sent him the very first evidence that acetylcholine occurs in the brains of mammals.